Okay, thanks very much for coming. So I'll tell you about some work on stochastic localization for the SK model. It's a algorithm, and it'll be joined with Ahmed and Andrea. So you may have seen Andrea around. So our goal in this talk at a very kind of high level, motivational level, is going to be that I'm going to give you a probability measure on Rn, and you'd like to generate a sample from it. And there are some examples of probability measures mu for which this is kind of a simple task from an algorithmic point of view. So if it's log concave, some kind of Gaussian looking thing, then you can run Langevin dynamics or various analogs and you'll sample efficiently. And it's of great interest to expand the range of distributions that can be efficiently sampled from. So maybe just think of things that look on the, like the picture on the right. Okay, we're going to focus on using models today. So these are going to be discrete distributions on the n-dimensional Boolean cube. And they'll be defined, as probably most of us know, by by an interaction matrix A, which is n by n, and it's telling you how the different coordinates of x, how the different spins interact, according to this formula for the probability up to a constant factor to sample a given vector x. So the picture, of course, is you have some atoms or some other objects, and they're interacting pairwise, and the entries A are telling me if they want to be aligned or disaligned. Okay. First algorithm you might think of, kind of ubiquitous algorithm or method is Glauber dynamics, where you repeatedly choose a coordinate, sample given all of the other coordinates, and this will mix rapidly if the interaction strength is not too strong. But in general, it can be slow. And today we'll look at some other methods for sampling.
So I'm not sure I understand that. Could you say again? Wait.
Like what I mean by Glauber dynamics. So it's just the standard Markov chain Monte Carlo. You just start with an arbitrary vector x. You look at maybe the first coordinate, you resample it. Yeah, just keep doing that for a while. Okay. So here's another way you could try to sample. So I'll give a couple of kind of strange algorithms that don't really make sense maybe, but serve as some motivation. So the first one is sequential sampling. And what we're going to do here is, I'm gonna say that, let's suppose I have a black box, an oracle, that tells me the mean of the distribution I'm trying to sample from. And it not only tells me the mean, but it tells me the conditional mean if I fix any subset of the coordinates, maybe just the first t coordinates for some ordering. Okay, then I can sample easily from my distribution by just sampling one coordinate at a time. So the first coordinate of the mean without any conditioning tells me the probability for the first coordinate to be +1 or -1. I set it at random, I condition on it, I just kind of repeat. Okay, this is great. But this oracle is really not something maybe we can hope to expect. How would I find this oracle? Maybe I would need to sample from my distribution in the first place. So there's some kind of chicken and egg problem. So it's not clear how helpful this is. But what I want to point out is that this is kind of a different way of thinking about sampling from a distribution as compared to a Markov chain. So in a Markov chain, you kind of just take a random walk around. You expect like the first steps to not matter at all in the future if you go long enough. Here I'm kind of like revealing information gradually, and any information I reveal is kind of permanently there with me. And there are other ways to try to sample in this kind of different flavor. Let me show you a second stylized example, which is a simple way to sample a uniform random variable between 0 and 1. And it's going to use something called Plato's urn, which is a very, very nice little story. So what's the idea? So P is a uniform variable between 0 and 1. What I'm going to do is I'm going to sample an infinite sequence of IID bits, like zeros or ones, which each have probability P to be 1. And I'm going to do this kind of without knowing what P is. So more precisely, if I know that P is uniform between 0 and 1, and I generate this infinite sequence of Bernoulli variables, there's some distribution for that infinite sequence averaged over P. And I can try to sample from that sequence while keeping P random the whole way through. It's just some distribution over sequences. P kind of formed by averaging different distributions over P. So if I can sample from this long infinite sequences, then I can use the law of large numbers to kind of retroactively recover P from my sequence. Does this make sense?
To me, it doesn't. I'm sorry. Maybe I'm out of it today. Could you try again?
Yeah. So like, let's say P is a half, then I'll have some distribution over infinite sequences. Let's say P is a third, I'll have some other distribution over infinite sequences. Since I know the distribution of P, I know how I'm supposed to average these different distributions over sequences. So I get one kind of big distribution over sequences. It makes sense to sample from this distribution over sequences without first figuring out what P is. If I can do that, then I can kind of recover the P that was associated with the sequence I found using just the law of large numbers. So if I can do this first part, then the P that I find in this way will be a uniform random variable.
I'm a little confused too. So are you assuming P is uniformly distributed?
Yeah, I'm assuming, well, I'm trying to sample a P which is uniformly distributed. So I'm going to think that there's some P which is uniformly distributed that I don't know. And it's going to be coupled to my infinite sequence. I mean, it's going to be determined by my infinite sequence.
The infinite sequence will have a P, or it will have a random P.
Yeah. So kind of it'll.
I'm not quite sure whether we're looking at superposition of different.
I guess it's like there's an adversary, and they somehow say they sample P from it random, and they sample this infinite sequence of Bernoulli P, and somehow you have to retrieve this P. You can do this just by large numbers.
So there's kind of an error going both ways. So if I choose a uniformly random P or a P from any other distribution, I get a law on sequences, right?
Yes.
Also, if I have a sequence, I can recover P kind of deterministically almost by just using the law of large numbers.
The question was whether the distribution of B1, B2, and so on is averaged over P.
Yeah, it is. Yeah. So that's the point, right? So because I know the distribution of P is supposed to be uniform, that gives me a distribution over here. Right.
It's just a distribution over distributions. So I think it was confusing because it says about 9P. So at least for me, I thought that meant P was fixed.
Yeah.
Yeah, sorry. So
but anyways.
Yeah, let me just try to say it one more time. So I want to say P is uniform.
Someone samples P and then samples the sequence, and then I want to somehow figure out what was P.
Yeah. So like, because we know the distribution of P, we know the distribution over here. We're just going to sample from the distribution over here, and then we're going to recover P.
So if P is like not uniform, then it still continues to hold, or?
Yeah, I mean, that would change the distribution over sequences. Yeah.
Because it holds like pointwise, right? In some sense.
Yeah. Okay, so the point is that you can do this, and it's not so bad. It's just the Laplace rule of succession. So given the first few bits, if I began with the prior that P is uniform between 0 and 1, I can determine the conditional mean of P. And that will exactly be the probability for the next bit to be 1. So I can generate my sequence of bits 1 bit at a time. It's just that the probability for the next bit to be 0 or 1 will depend on the number of, on the statistics so far for my sequence. Right, so if I see mostly 1s, then my next bit should have a higher chance to be 1 because I think P is larger. And so you can sample a long sequence like this, and then you can use the law of large numbers, maybe cut off at some finite approximate point, and instead of going all the way to infinity, and you can kind of sample infinite. You can kind of sample a uniform random variable this way. This is not a good way to sample a uniform random variable, but it's something you can do. Okay, so the stochastic localization scheme we're going to be thinking about today is going to be in a similar flavor. So recall we have some distribution U, which will be some kind of Ising model distribution, but it's just some probability distribution on Rn, maybe compactly supported. I'm going to, instead of thinking of an average law over sequences, I'm going to think of an average law over paths, given by doing a Brownian motion with drift in the direction of x star, which is a sample from my distribution. So this is an n-dimensional diffusion process, and there's going to be a similar story where we can try to sample from the average law over paths and then read off the drift. So if I can, in the same sense as before, simulate this Brownian motion with drift without ever knowing exactly what the drift is, I can read off approximately the drift.
Can you please go over what exactly is this?
Oh, what is what?
Everything.
Yeah.
So mu is some compactly supported distribution on Rn.
Okay.
X star is a sampler from it. Yt is a Brownian motion with x star as its drift. Is that okay?
So T is time and BT is.
Yeah,
BT is a Brownian motion.
BT is a standard n-dimensional Brownian motion. So at time t, this is a Gaussian with covariance t times the identity and mean t x star.
That's the only variable in that equation.
So both x star and BT are random, but you maybe think of so there are again two ways to think about it. You can first sample x star and then do a Brownian motion with a deterministic drift, or you can then average this distribution over continuous Brownian motion type paths over the initial choice of drift.
What are you trying to sample here? What is the goal?
We're trying to sample x star from U.
X star from you, this is what you're trying to sample.
Yeah.
You have access to YT? That's the assumption?
Right, so like what happened here was that we wanted to sample P. We generate this sequence which has a distribution depending on P. We sample from the overall distribution of the sequence, and then we can back out P at the end. So it's the same goal here.
So you're saying that even that you don't have X star, for some reason you will be able to sample the YTs.
Right, so the goal is to be able to simulate the process YT without knowing what X star is.
I guess another way you can think is that BT is some sort of noise and you're trying to figure out how to remove it.
Yes, but the thing is that you don't really have access to this process, but you have an access to a sample from this process and you want to recover X star from this sequence of YTs.
Yeah. So like, I guess another example you can imagine is, let's say X star, let's say we're in one dimension, so X star is just plus or minus 1. So YT is just a Brownian motion with an unknown drift, which is either +1 or -1. So maybe, you know, it's kind of going like this, and then eventually it kind of starts choosing a direction. So it's not such a crazy process to sample from. I'll say kind of something equivalent in a minute, but kind of at any point, it's just a Brownian motion with a drift, and the drift just depends on where it is. Like it's a very reasonable diffusion process. Like when you have a Brownian motion with an unknown drift, it just averages out to a Brownian motion with a reasonable drift. So So kind of like what happens on the level of paths is that like if I don't know X star, then I know that in the next little bit of time, I'm supposed to add some Gaussian noise plus a little bit of X star, which I don't know. So what should I do? Well, I should just kind of, if I don't know X star, I should just add the conditional mean of X star given what I know so far. So these are going to give me the same law in paths. It's kind of the same as in the Poirier story. So if right now I think X star has like a 90% chance to be pushing me right and a 10% chance to be pushing me left, then I should just average those and get what, like a 80% push to the right. That'll be kind of my overall drift Indian yield distribution. Yeah.
But you have to know something about mu. To start off, you have to know the average of mu, and also later on, maybe you need to know a bit to calculate these conditional expectations.
Right, exactly. So it's not clear that this is any easier because we need to understand mu because we need to be able to figure out what
the advantage of this is at the moment.
Yeah, right. So it'll turn out that for the model, I'll be focusing on this does work, but it's completely not obvious that this is gaining anything.
Yeah. So why is it called stochastic localization?
Right. So when Albon is using it, he's kind of thinking about it in a different way. He's not focusing so much on the paths. What he's focusing on is at any time t, if I reveal this information, then I kind of my initial distribution mu for X star has some posterior. Like I learned something about it. And so I get some new distribution mu t. Mu t will localize. So it's kind of, you have a martingale on probability measures. It'll start at mu. It'll eventually localize around a single point. It'll kind of become more log concave over time if it starts log concave. In convex geometry, there are various...
It's kind of a regularization that you're doing of the distribution mu when you add this Brownian motion?
Yeah, it's kind of smoothing it out.
It's smoothing it out, right?
Yeah.
And then trying to extract information through the smoothing.
Right.
Well, it might not be concave, but after I do the smoothing, maybe it becomes more accessible.
Right, yeah. Yeah, so like some of the ways it's been used are like that. You want to show a functional inequality for a general log concave distribution. You smooth it out a little bit. You say it didn't change too much, but now it's strongly log concave. Yeah, good. In this generality, they can work with some processes that are a bit more general. Like they can have a general time-dependent covariance and things. But we're just looking at this specific form. Other questions about this? Okay. Right. So basically, what we'd like to do is just understand how to simulate this. So it's just a Brownian motion with a drift that depends on time and space. And this drift is exactly the conditional mean of X star given what we've seen so far, kind of, where we think X star is some underlying drift. So if we've so far been moving in some direction, then we think X star is more likely to be pointing in that direction. And there's a precise formula for it, which is this. So basically at any time t, our current distribution for X star is our initial distribution with some exponential tilt.
You're basically convolving it with some kind of heat kernel, right?
Yeah, exactly. Yeah.
How is this different than what you needed to do the Markov chain? Because if you can, under any conditioning, get the expectation, wasn't this enough for doing this with the Markov chain?
Right. So it's similar in flavor. It's kind of just you're not doing coordinate by coordinate. But yeah, it's definitely similar in flavor. It just,
I'm asking, is this a weaker thing you need about the distribution, or do you need the same condition about the distribution to be able to compute this?
well, it's a different kind of information, I guess, right? Because it's just, in both cases, you kind of would like a conditional mean, at least approximately, but in one case, you're conditioning on some coordinates. In one case, you're revealing kind of Gaussian information about all the coordinates. But yeah, I mean, they're very similar in flavor.
Is it clear that it only depends on the endpoint, yt, when you condition on all the past up to time t?
Yeah, it's a Brownian motion with a drift. The endpoint is kind of a sufficient statistic.
For the drift.
Yeah. Right. So yeah, that's a good point. So we have this whole path history, but we only actually care about the current position, which is, of course, very convenient. Okay. So let me continue and say what the model we're going to be focusing on is. Maybe let me just say we're actually going to discretize, of course. So I'll only mention it at the end, but there are some technical issues about discretizing that you, of course, have to take care of. But here's what the algorithm looks like. It's just a discrete time diffusion, and then you maybe round into a corner at the end. Okay. And again, okay, we'd like this conditional mean. That's what we want. It's really not clear that we've gained anything, as has been pointed out. But we'll see that it does gain us something in a specific model, which is the Sherrington-Kirkpatrick model. So what's the model? So it's
would it be useful for just the easy model? No ordinary, let's say nearest neighbor without any useful in this context, or is it really somehow mostly adapted to these field models?
So I think, so one of my collaborators said he is working on some version of this where maybe if you have, so maybe you're on a lattice and you have exponential decay of correlations, then something related should also make sense. Maybe the goal is to say that you have a factor by ID sampling procedure. Yeah, I think it in principle makes sense in a lot of models.
Actually, can you say something about why it depends only on the what? Can you say something about why it depends only on the last point yt and not on the entire sequence?
Yeah, so it's just so I'm doing a Brownian motion with some drift.
Yes.
Right. Okay, and I observe this for some interval of time. The drift is the endpoint is a sufficient statistic for what happened, right? There's just if I think of how the law of my path changes depending on this drift, it's just some function, it's the difference between the endpoint and starting point rates.
It's not completely clear to me, but I'll believe you. In terms of not having more information.
You want to know why it's a martingale? Is that what you're asking?
I was asking is why is the conditioning on everything that happened so far is the same as conditioning on the end.
But the same as asking.
Okay, so if I say Gersonov, that doesn't help probably. Or,
yeah, okay, but that's
fine. What's cal f sub t?
Sorry, that's just some filtration up to time t. So it's just conditioning on everything up to time t, like the path and so on.
It's the same filtration that you do with Brownian motion. It helps.
Well, I guess it just depends on t is the point.
Yeah. So what I'm saying, this is exactly saying that it just, all we care about is kind of the current position yt and not the whole path.
X star doesn't change with t, right? X star is given. So X star is completely independent of FT, and DT is adapted to FT.
I keep forgetting. I
And
think of it sometimes that way.
BT is a Brownian motion, which means that conditioning on FT is the same as conditioning only on DT kind of point. So then, and X star is completely independent of that, so that's not going to change the condition.
Can you also say what GOE is?
Yeah, I'm about to. Yeah. So it's just right. So what we're going to look at is using a model with a GOE coupling matrix, and that means it's a Gaussian symmetric matrix. Entries are IID except that the matrix is symmetric, and the variance of an entry is 1 over n. So the entries have order about 1 over root n.
That's stand. What does it stand for? Just out of curiosity.
Gaussian orthogonal ensemble. So the point is that it's invariant in distribution if you apply an orthogonal like rotation matrix. Kind of the canonical random symmetric matrix. Okay. So just to be clear, our goal is that I'm going to give you a GOE coupling matrix G, and I'd like you to generate a sample for me from the corresponding distribution. And I'll of course also give you the value of beta. We'd like beta to be of constant size. That's kind of the scaling that is usually interesting. If you plug into some kind of basic condition for fast mixing of Markov chains, then you'll see that Glauber dynamics, the guarantee you get in that way is much weaker. It's going to be off by a power of n. So it's kind of not. So what that means is if you try to do a coupling argument, then your coupling argument will not really work very well here at all. Okay, so let me just to give a brief history. So the Ising model is quite old, of course. The SK model is about 50 years old. It's a model for disordered magnets where the interactions between pairs of atoms is kind of random and not so nice and ferromagnetic. So Parisi gave a non-rigorous solution based on replica symmetry breaking, which recently won him a Nobel Prize. There's been a ton of math on this model since then, including Talleyrand's proof of the Parisi formula for the free energy. So we know a fair amount by now. This model is kind of not an isolated point in the space of models. There are a lot of other related models like random max cut and random ksat that are expected, but maybe less successfully proved so far to exhibit similar behaviors. One nice example I like to mention is that if you look at a random sparse graph where the sparsity is growing slowly with n, so lambda is maybe log n or something, this is an Erdi-Schrödinger graph, then the max cut value is it's half the number of edges, that's n over 4, and then the next order term has a constant, which is like the ground state of the SK model, and it's kind of implausible to get this constant otherwise. Okay, so what's known about sampling? It's somewhat less than for things like free energies. What you expect is pretty simple. You expect that efficient sampling is easy when beta is less than 1.
Sorry, can you go back to the previous slide with this Dembo Montanari? So this is so you have the graph is getting sparse with.
Yeah, you should think lambda is growing with n, but slowly.
Okay.
So the typical degree is like log n.
Okay. Yeah. And if I make it grow faster than I can, then is it too hard to compute?
I think that's also sort of fine. Like if you have half the edges there, it's also gonna be fine.
So it doesn't depend upon lambda particularly, or I mean, is that function, how general was that function? You got a scaling by n, right? The edge weights are going down by a factor of 1 upon n.
So basically, if lambda is a constant, then
any constant,
it won't be wrong. Sorry, if lambda is a constant, then it will be wrong. It'll get more accurate as lambda
grows, and then it could be wrong.
If lambda grows with n, then it should be correct. Yeah. Kind of, I don't know, it's this kind of, once lambda is super constant, it kind of is the same as fully connected. That's the point. Okay. Yeah, so for sampling, what you expect is pretty simple. So for beta less than 1, so when beta is smaller, the interactions are weaker, so you expect sampling to be easier. When beta is less than 1, the model is replica symmetric, whatever that means, and so sampling to be easy. Beta is larger than 1, one expects it to be hard.
It's impossible. What do you mean?
You know, NP hard or something like this. I mean, it's a random problem. It's a bit hard to argue about NP hardness, maybe, but we shouldn't be able to do it, right?
I mean, you can't prove that, isn't it?
Yeah, right. So we have some results in that direction, but it's it's much weaker than anything about NP hardness. So there was a lot of very recent progress on this, which was really amazing, where it was shown that Glabro dynamics mixes rapidly. In fact, in kind of the optimal mixing rate, when beta is less than a quarter. These results actually only use spectral bounds on the coupling matrix. It's just anything where the max eigenvalue minus the min eigenvalue is bounded. So this is much better than what I mentioned before for the Debrucian uniqueness condition. There's a very recent result for tensor analogs, the mixed p-spin models as well, which is a lot more involved. It's not just some simple spectral bound that's needed. And this is for like sufficiently small beta, sufficiently high temperature. What I'll talk about today is how to use stochastic localization for this model. We'll get a sampling algorithm that succeeds in a weaker sense, all the way up to beta less than 1. Actually, originally our result was for beta less than a half. There was a technical improvement that I'll mention by Michael Solentano that made the same algorithm work all the way. So the metric for our guarantee is Wasserstein distance. So it's much weaker than total variation. Basically what it says is that I'm gonna consider 2 points, 2 vectors in the cube to be close if they agree in most of their coordinates and like 99% of their coordinates. So that means like this is small. And then I'll say that 2 probability distributions over the cube are close if I can couple them together so that usually the coupled pair of vectors is close together. Basically it means that I have kind of agreement in most coordinates under an optimal coupling, and we'll consider such pairs to be close. So our main result is that for any beta less than 1, there is a efficient sampling algorithm which succeeds in with high probability and expectation, and at getting a normalized Wasserstein error less than any epsilon.
And what is this expectation on? Is it on the G?
Yeah, it's over G. Yeah, exactly. Great. So this mu alg is kind of compressing all of the randomness in the sampling algorithm. So the only randomness for the expectation is just the random matrix G. So for some G, this will fail horribly because we're really going to use the randomness, but for most choices of G, it will work well.
And you have some understanding of what is the property of G that is required? If I give a general matrix and you write like a list of conditions, if it satisfies that, then it works, or?
So the algorithm is going to use approximate message passing. So that means that we're going to repeatedly multiply by G and argue some kind of like repeated central limit theorem for the entries of the product you get. So it's a,
okay,
maybe you can,
that's something.
Yeah, it's something.
Could you tell me again what was known before this?
Yeah, so the previous results were basically for Glabro dynamics, and they were getting fast mixing for beta, which was not too far off from what's expected, but there was some gap. I mean, I think you expect that Glabro dynamics should work in the full high temperature regime, but it seems difficult to prove. Yeah. So this is a different sampling algorithm, but the guarantee is a little weaker in some sense, but better in some other sense.
But their measure of distance was different, or was it the same one?
They're doing total variation mixing. I mean, yeah, just fast mixing Markov chain.
So you don't get mixing?
Yeah. So I mean, this isn't a Markov chain, right? So it's a weaker sense. It's
Yeah, the
Wasserstein distance, and yeah, it's not clear if there's a way to argue that maybe if you do Glauber dynamics starting from this, then you should mix fast. It seems like a natural thing to hope for, and I'm not sure it's true ever.
Do you think the n squared can be improved to n log n?
Well, there's n squared entries in the matrix. So we're basically multiplying by the matrix like a constant number of times. So yeah, I think there's not, that's not something that can really be improved. Okay.
Wait, sorry, one more time. Can you go back one more time?
Yeah.
So epsilon is,
here.
So how is epsilon compared to the beta?
So it's,
yeah, what is the epsilon?
So it's just for any beta less than 1 and any arbitrarily small epsilon.
And then you take n large enough.
Yeah. Yeah, the thing is, n has to be taken very large, given those guys. Yeah.
Really, you're saying this expectation goes to 0. For fixed beta, this expectation goes to 0 with n. Probably that's what you're saying.
Yeah, I mean, technically the algorithm depends on epsilon too. So
You could have a number of steps.
It's an epsilon dependence in the algorithm, in complexity.
Yeah. Okay. Okay. Yeah. So there's let me make a couple remarks on stability and hardness before getting into the algorithm. So the algorithm has some nice properties that give some nice corollaries. The main thing is that it's stable with respect to its input. So it takes in this coupling matrix G, as well as the inverse temperature parameter beta. And it's only going to use a constant depending on beta and epsilon number of matrix vector products, basically. So this means it's kind of stable. And one way to say this more precisely is to take a small perturbation GS of my coupling matrix. So I'm going to construct GS as a kind of interpolation between two independent copies G0 and G1. So if I think that S is very small, then GS is some very small perturbation of G0. Right. So I can think of what my algorithm does on these two different inputs, G0 and GS. They're both distributed according to the same GOE law. They're just coupled to be close. And the stability means that if I take this S to 0 and then N to 0 limit, the Wasserstein distance between the algorithmic outputs on these two different Gaussian matrices is going to be small. Maybe just to say a bit about the limit. So first off, if you switch the order of limits, then this says almost nothing. If you take n to infinity on the outside, then this just kind of says you have some very weak form of continuity or maybe even measurability. But if we take s to 0 on the outside, this actually means something. It means that if I perturb my input by 1%, and then I take n very large, my algorithm should still behave kind of similarly on these two matrices.
And you don't expect this for beta greater than 1. I mean, you also don't expect the actual.
Yeah, exactly. Yeah, you're predicting the next slide. Perfect. Right. So this has a purely structural consequence. It says that the true Gibbs measures are stable in this Wasserstein sense, just because you go around the square. So if you have this is close to this, this is close, this is close. And this is not true, as Ron was saying, when beta is larger than 1, which is kind of, which gives a hardness result. So what do I mean? I mean, if I perturb, if I make S a small constant, then this Wasserstein distance between the two actual Gibbs distributions will not go to 0. So this is a combination of two nice things. One is Chatterjee's disorder chaos. It says that if I take independent samples x0 and xs from G0 and GS, then they'll be approximately orthogonal for any beta. And replica symmetry breaking, which basically says that if I take two independent copies from the same Gibbs measure and beta is larger than 1, then their inner product will not go to 0. This is almost the definition of replica symmetry breaking for here. So if you put these together, what you find is that when beta is larger than 1, no stable algorithm is able to sample even in this weaker Wasserstein approximate sense from the SK Gibbs measure. So this is, it's not NP hardness certainly, but it's some result that suggests that sampling should actually be hard past beta equals 1. And it does hold for some natural algorithms, such as the ones we use and kind of things of a similar flavor.
But this result only holds for your algorithm when you're discussing, or for all algorithms? I mean,
so it holds for any algorithm that has the same kind of stability property. And this kind of stability property will hold for kind of things of a generally similar flavor. If you do things like Langevin dynamics.
So no stable algorithm.
Yeah.
Will work.
Yeah, no stable algorithm. Yeah. So you can think things like doing Langevin dynamics on a short time scale. Things like this. But even if you do like some kind of Langevin dynamics or Glauber dynamics on a polynomially large time scale, it probably won't be easy to show it's stable at least. So it's certainly not the endpoint for showing hardness. Any questions about this part? Okay, so let me just say a bit about the algorithm. So again, basically I have this SDE, and what I'd like to do is estimate repeatedly conditional means of my my unknown X star drawn from the SK measure under some site information YT. And the solution involves a few ideas. There's kind of a two-phase procedure. So I'll kind of just run through these so you can see how it works roughly. So the first stage is a rough estimate using approximate message passing. And then for technical reasons, we need to refine it to a higher accuracy estimate. So kind of where do you get started trying to do this estimation? Well, there's kind of a naive mean field equation you can write down when you're in a situation like this, which is that MT should, the mean at time t should satisfy this, this kind of fixed point equation. So where is this coming from? Well, MT is being sampled from Ising, or XT is being sampled from Ising model. So each coordinate of XT is kind of exerting some influence on all the other coordinates. And if I look at beta G times X, then I get kind of the effective field being exerted on each coordinate. And YT will have a similar interpretation. It's kind of an external tilt by a magnetic field. So this beta GMT plus YT should maybe be kind of the effective field that my that is felt by X. And then if I want to convert from an external magnetic field to an expectation, I should apply a hyperbolic tangent.
So YT is acting as a magnetic
yeah,
as a magnetic field.
Yeah, that's basically how it enters. Yeah. The distribution for YT is a bit complicated, but once you see YT, it's just acting as a magnetic field. Okay, so this equation is not actually right. Basically, you should actually put X inside the hyperbolic tangent instead of the mean. So kind of we took the expectation too early. We can't really do that. But it turns out there's a way to fix this. You can just imagine you Taylor expand hyperbolic tangent and make some guesses for what terms to keep, and you'll get the tap equation where there's kind of a similar flavor, but there's a correction term. Okay, and once you have this tap equation, there's a way to kind of solve it as an algorithm where you turn it into a recursion and you just iterate until you get to a fixed point. So here I've inserted some time indices, k plus 1, k minus 1. So you can start with some simple initial choices and just run this repeatedly. And hope that you get some kind of convergence.
Using the Bolthausen?
Yeah, right. So this is something Bolthausen introduced. It was kind of, I mean, in a very slightly different context, but yeah, it's almost what Bolthausen did. This is what an approximate message passing algorithm is. And you can think that this extra funny term is kind of ensuring that we get some non-backtracking property. So if you think of G if you think of doing belief propagation where G is kind of the weighted adjacency matrix for your graph, then multiplying by G is almost like doing the belief propagation step, but belief propagation is supposed to be non-backtracking. So you can imagine there's some correction term you can add in to tie everything together. Right, so by now this is kind of a major tool for these kinds of problems and others. And there's some technical difficulty for us because the distribution of YT is kind of complicated. So if you can imagine that if the matrix G is totally explicit and I just tell you some iteration like this, then you can just explicitly work out how it behaves. But the SK Gibbs measure is entering and choosing X star, which goes into YT, which enters here. So it's not so obvious how to analyze this. Okay, maybe I'll just say briefly. There's some trick to do this where you use contiguity with a simpler spiked model. So you change the distribution to do this analysis, and then you argue that things happen with high enough probability that you can transfer them.
What's AMP again?
Approximate message passing, sorry. So just this kind of recursive iteration. Okay, so just to be brief about it, so we have this formula for the law of, this is the formula for the SK Gibbs measure. You can think of sampling X star and then G, and using this as the formula for the law of G given X star instead of vice versa. This will change the distributions of things, but you can imagine it doesn't change the distributions too much. And it has a couple nice properties, namely if G is sampled this way given X star, it has a very simple spiked distribution. You're just kind of shifting the distribution of G. So this makes things very explicit, and it turns out to not change the distribution too much. There's some kind of contiguity statement. And this means that you can do your analysis on one side and then say kind of anything you can prove also holds on the other side. Once you do this, there's kind of an explicit description for what happens for AMP. And the idea is like this. Let's say I have two vectors V and W that are just independent of my matrix G. And I think about multiplying both of them by G, which is a Gaussian matrix. So then basically these two vectors I get should each have IID Gaussian coordinates, but they should be correlated. So the first coordinate of GV and the first coordinate of GW should be correlated if V and W were correlated as deterministic vectors. And so what you want to do is say that, okay, every step of my recursion, I'm multiplying by G. So I can track how correlated each of my iterates are with each other in a recursive way. So how correlated should this new K plus first iterate be with the previous ones? Well, I got it somehow by multiplying by G. So I can just go back one step because the correlation between V and W should kind of agree with the correlation after multiplying by G. So there's some recursive way to track things. And this extra Onsager term exactly lets you do this, even though you're using the same matrix G over and over. So you can't directly argue that multiplying by G is going to preserve correlations after you've already done it. But there's some way to to say that actually the ensemble term lets you do this argument. So you just get a very explicit description, kind of coordinate by coordinate for this recursion. And kind of the upshot is that you can read off the mean squared error of your estimate that you get this way. And then you can use something called the MSE Area Law to show that you actually found the right thing. So this is, so I skipped ahead a bit, but there are some formulas. You get a formula for the mean squared error between your AMP estimate and the kind of a Gibbs sample from your SK measure. We'd like to show that we found kind of the true posterior mean. So what we'd like to do is find the true mean squared error of the posterior mean, which is going to minimize the mean squared error. And we'd like to show that we got roughly this mean squared error. The point is that there's some area law that tells you what is the integral of the mean squared error as you vary the value of t. So as you vary kind of the signal to noise ratio in your side information yt. And if you can check something like this holds for your estimates, then you kind of saturated this bound, so you know that you found the kind of asymptotic optimal mean squared error and hence the posterior mean. Okay. So all of this stuff gives you a rough estimate of this flavor. So for any epsilon, you can get a good approximation up to epsilon relative error. Okay, and then this turns out not to be quite enough. So I just want to say that this is where Michael's, if improvement comes in, we needed some potential to be strongly convex. Michael showed that it was for beta less than 1, whereas we only did it for beta less than 1/2. So this potential is something that is going to have kind of a approximate minimum at the point we're interested in, and finding an exact minimum is some refinement procedure that helps a lot. Sorry.
It's only convex near this point, is that correct? Or
Yeah. So there's some,
not globally convex.
Yeah, it's just potential. It's just, it's a potential that's strongly convex just in some little neighborhood.
But that, of course, helps you a lot.
Yeah.
Because once you're closer, then you know where you are.
Yeah. So if there's some technical reason, it's very helpful. Okay. Great. So that's it for the algorithm. So it's a bit technical. There's some nice ingredients that had to come together. I just want to say that it actually turns out to be kind of similar to real algorithms, which was a bit surprising for us. So what this says is that if I go back, basically I want to denoise, if I want to be able to add Gaussian noise and compute a posterior mean estimate. And then I can run my sampling algorithm. This is basically what image generation models do. And it's how you generate pictures like this. So the setup is a bit different because they're kind of using data to estimate they're learning from data instead of using like high dimensional statistics types of stuff. But the high level approach of kind of running a diffusion process is kind of doing almost the same type of method.
I'm confused about what's the distribution of images that you're.
Yeah, I don't have sense.
Right, sorry. So the point is you have some images.
There's no assumption. This is just what they do, and you're saying
they're noise, but you have noise on them, or
yeah. So what you can think of is So I give you these images. For each one, I turn it into Gaussian noise by doing an OU process.
So are you trying to find the natural images? Are you after noise, or are you trying to denoise it or not? I'm trying to.
Sorry. Yeah, let me go. So the story is I'm giving you a data set with 1 million images, and you'd like to be able to generate new images.
Oh, new images.
Yeah.
From the distribution that those are drawn from.
Yeah. So the way you do this is you run an Ornstein-Uhlenbeck process on your images in your data set to turn them into Gaussian noise. And then you try to learn the time reversal of this SDE, start with some new Gaussian noise, and time reverse it back into a new image. And it's
so you want to construct another natural image.
Yeah.
That's roughly from what you have.
Yeah.
So you noise it, then you do some minimization, and then that enables you to get an idea of what your distribution was.
Yeah. So for us, so what I was talking about was like YT is TX BT, right? And if you just kind of rescale things, this is basically the same as an OU process. Like here, you're kind of turning Gaussian noise. Like here at time 0, you have pure Gaussian noise, and at time infinity, you have no Gaussian noise. And an OU process is kind of the reverse. So it's like it's parameterized a little bit differently. Okay. So I just want to say that there are some results on this. They kind of, generally are going to need stronger assumptions. For us, we have some kind of high probability statements happening in quite a few places. So it's a bit more subtle to get things to work. Okay, here's a summary of what I talked about. There's a general way to sample using stochastic localization, and it works for the SK model. And we were able to get approximate sampling in this Wasserstein sense for beta less than 1, and had some evidence of hardness for beta larger than 1. One thing I want to highlight is that it seems that if you're in some related models, we don't expect just copy pasting this to give a sharp threshold, because even if you have like a spherical p-spin model, so just think instead of a quadratic interaction, you have like a 4th order tensor interaction, and maybe you're on the sphere, there should be some kind of shattering. So basically, so it means the Gibbs measure should break up into an exponential number of little clumps. So basically, we expect that our proof that we expect like replica symmetry breaking to kind of always lead to hardness, but it may not always be possible to sample in the full replica symmetric phase. For the SK model, there's this phase just doesn't appear, but sometimes it does.
So are there other models for which you expect this algorithm to work fairly well, or?
Yeah, I think it should be something that works in a fair number of cases. So there was actually a work by Alan Sly and Danny Nam and Lim Fuzhang which was also of a similar flavor a bit before. They didn't write it this way, for sampling from using model on trees using as a factor of IED. Yeah, I think so. Andrea has some work in progress. There's some other works in progress on this. Should work in a few models. Yeah.
So it's a question for the end. If I gave you a sub-exponential time, but you could go super polynomials, maybe e to the root n time, would it be much easier? Can you then do more than you can for a polynomial time? Would anything improve? Can you do global?
Yeah, I'm not. I don't think anything is coming to mind. But I think it may be that then Glabro dynamics could even mix at low temperature. It's
with the e to the root n time.
It's not. Yeah, I think.
Yeah, there is the conjecture is that the mixing time of Glabro dynamics at low temperature is e to the certain power of n.
Okay.
But with n power less than 1. But it's kind of.
So things will improve.
Yeah, for this model. But for instance, if you take pistil interactions, then it's supposed to be, actually it's known to be to the n at the temperature.
Yeah, so a lot of variants of this model will have some overlap gap property where there's kind of some way to identify a free energy barrier that will lead to exponentially slow mixing. But the SK model is supposed to have full replica symmetry breaking, which means that those kind of don't exist. I think there isn't. I haven't been able to find any like nice lower bounds for Glabro for SK model, even at very low temperature, actually. Right. And, okay, thanks very much.